Hi folks, welcome to part 2 of the lesson. So here we're going to take a look at the vector equation of a line, this time in 3D. So what we're going to see is that our method for the alternate definition for the equation of a line in 2D does generalize nicely into 3D. Okay, so I'm just going to go through what I did before. So here I've got now, again, I'm going to make no effort to be exact, but this is just as a guide. So I'm on my XYZ 3 space here, and I've got some line. Okay, so the way in which we describe the equation of the line is, first of all, by using a vector perpendicular to the line, which again, we'll call this a direction vector M, and then having any point on the line, say X naught, Y naught, Z naught. Okay, and in particular, we're going to look at the vector going from the origin to that point, x naught, y naught, z naught. So this is going to be our r naught vector. Okay, and by taking that r naught vector and adding to it some multiple of our direction vector, okay, so some multiple times our direction vector, we get to any point on this line. Okay, and so this represents our vector r, so the vector from the origin to any point on this line. So had I added a larger multiple, I would have gotten to a further point. I had added a multiple smaller than this one here, I would have ended up somewhere in between. Had I added a negative multiple of this direction vector, I would have ended up somewhere on the other side. Okay, but by knowing this one direction vector and that one given point, I can generate all the points on this line. So very similar to how we used a point and a slope in 2D to generate the line and slope intercept or standard forms. All right, so let's write this all out. So the equation of the line, as before, is given by vector r is equal to the vector r naught, so the vector to a given point on the line, plus some multiple of this direction vector. All right, and here t can take on any real number. All right, so this is what we call the vector equation. Okay, but if we take this vector equation and we write it out with the component vectors, okay, so here we have vector xyz, which is our vector r, is equal to the vector to the given point x naught, y naught, z naught, plus some scalar multiple of our direction vector, which we'll call ABC. We can now rewrite this in terms of the individual components. In other words, what we call the parametric equation. So here we have x is equal to x naught plus at, y equals y naught plus bt, and the z equals z naught plus ct. Okay, so here we have our vector equation. Here, t can be, again, any real number. Here we have our parametric equation. Okay, and we'll talk a little later on as to why this version of the equation is of particular importance. Okay, there is a third way of representing the equation of a line, not used quite as often, but I'll show it to you just so that you're aware of it. It does show up in the textbook. And here we notice that in our equation for in the parametric equation of the line, we see that they all contain the exact same parameter of t. So I use the same t value to find the x, y, and z of a particular point on this line. Okay, so what we can do is we can isolate for t. Let's see what happens. So if I isolate for t in that first equation, what do I have? I have x minus x naught, okay, and then divided by a. Okay, but I can do the exact same thing in the second equation, and it's still going to be equal to that same t value. So I have t is also equal to y minus y naught all over b. And same thing in the third equation. That's equal to z minus z naught all over c. Okay, and so this system of ratios, okay, the difference in the components over their specific component of the direction vector, this here also generates all points on the line. This is called the symmetric equation of the line. All right. So the idea here is to be able to identify what the different components of these equations represent. So let's come up with some examples here. Okay, and I'm not gonna make any effort to make them all the same. So let's say I'm given something in vector form. So let's say I have r equals 1, 2, 7 plus t times -3, 1, 5. Okay, you should be able to determine based on the fact that this vector here is multiplying the t, that this represents the direction vector and this represents the specific, or the vector to the specific point on the line. All right, say I've got something in symmetric form. Say I have x is equal to -2 plus 3t, y is equal to 7 minus t, and z is equal to 4t. All right, you need to be able to identify that -2, 7, and since there's no constant term, so it must be 0, that -2, 7, 0 is the given point on the line, and that looking at the coefficients of t, in other words, 3, -1, 4, it represents the direction vector. Okay, or if you're given an equation in this form, so x minus 2 over 7 equals y plus 3 over 6 equals z, okay, that you should be able to identify that these numbers in the numerator represent the point on the line. Okay, so what is the point? Well, here it's x minus x naught, so x minus 2, so it's 2. Here, y minus y naught, so here, because I have y plus 3, it must be y minus -3. Okay, and here it's just z on its own, so it must be z minus 0. So this is the point on the line, and the direction vector is just represented by the numbers in the denominator. So it'd be 7, 6, and this is z over 1, so 7, 6, 1 would represent the direction vector. Okay, so just to recap here, understand the diagram to see how these equations come about. Vector equation, vector to a point on the line is equal to vector to the specific point plus any multiple of the direction vector. Parametric equation is the exact same equation, just the individual components written separately. And then the symmetric equation is when we've isolated for t in all three and equated the expressions. But you shouldn't have to go from here to there. You should be able to identify just by looking at it that these numbers here represent the components of the point, and that these vectors here, these values here represent the components of the direction vector. So values in the numerator, point, values in the denominator, direction vector. Okay, that's it for this one.